programs. And it's our pleasure that Professor Soumendu Laha, who is a very eminent researcher in scientific computation domain, will share his views today. Professor Laha joined Indian Institute of Science, Bangalore in 2003 and is currently a professor in Department of Computational and Data Sciences in IISc. Professor Laha did his PhD in scientific computation from University of Minnesota, Minneapolis, USA. Before joining IISc, he was an assistant professor at the North Dakota State University, USA, an advisory software engineer at the IBM Corporation Microelectronics Division, East Fishkill, New York, USA. His research interests include computational study of stochastic differential algebraic and steep stochastic differential equations, partitioning, stability, and stochastic study of dynamic complex networks, data assimilation and inverse problems of stochastic and constant dynamics, mathematical softwares for control and direct optimization for high index differential algebraic equations, etc. He is one of the leading scientists in this domain in our country, and it will be our great privilege to host him in this workshop. Professor Laha, please.
Okay, thank you for the kind invitation. And so I'm going to present something that is an ongoing work, but I just thought that it would be maybe an interesting thing give a heads up like on what we are doing currently in our group. So I'm going to talk about this, the spatiotemporal propagation of reaction-diffusion equation in a complex network and related sparsification of graphs. So sparsification is an important problem in data science, and the most recent result being the result on Kadison-Singer problem, which used to be a 60-year-old open problem, and this was resolved around 2013-14. And so with the resolution of Kadison-Singer problem, the sparsification thing and actually application of the sparsification to more realistic data science problems became feasible. And in that thread, we are attempting this, this talk actually. Okay. So. Okay. Okay, we'll go through brief outline is like this, we'll go through some preliminaries, discuss a little bit of the literature that is out there, and then we'll discuss a framework for creating score spectral graphs of certain undirected and unweighted graphs and interlacing the characteristic polynomial. So this is similar to the Cauchy interlacing problem that we have in linear algebra, and to bring it into the spectral theory of this reaction diffusion graphs or these complex networks, finite complex networks. And then we'll discuss an approach to this sparsification via a Steiner tree kind of approach, Steiner tree, some technique that is from the Steiner tree problem. And this is useful for looking at the spanning trees that we want and for our sparsification. And finally, we'll give a procedure which uses the proper orthogonal decomposition. Remember, we have a dynamics out here because it's just not a static graph. So you have a reaction diffusion phenomenon going on, and connect it to the the 4D var method to approximate the flow in the complex network using the spanning trees that we got from the Steiner tree kind of approach. So this work is a joint work with my current student Abhishek, and the most of it is like most of the ideas that you will see are evolved with him and are his contribution. So so we consider a complex network, and the graph induced by the complex network, and we can just put it out there. Is it features the pattern of connections, and you can see, and it can be purely imaginary and random as you know, as things can be. For example, a complex network induced graph is like a Erdős-Rényi is well known. So this kind of thing that we are going to consider. And well known in that is a Laplacian of a graph. So which is nothing but the diagonal weights and minus, the basically which is nothing but the degree of the graph, and it is subtracted, the adjacency matrix is subtracted from it, and we get the Laplacian of the graph. But however, the Laplacian also means like how a diffusion works on a graph, like so it is similar to the like in the in the context of vector calculus on networks and discrete vector calculus on the network. This this is so the Laplacian is like a diffusion operator. So we use the usual definition. So if like an element uv, like like the u and v are the vertices, yes, like belonging to the vertices, the set of vertices in the graph, and if u is equal to v, we have the degree of the vertex. Yes, v, and if not, then if u and v are adjacent, we simply put a -1 and 0 if they are not connected. So now we'll come to the kind of now we will come to the kind of problem that we would like to look at, and so here, okay, so there is so before that, like we can also like construct a normalized Laplacian. So this is useful, like if you have this in the complex network sense, and if d and du and dv are typically large, so and so this works in that context. Okay, so then. And we'll come to the problem, like so this is a reaction diffusion problem, we said, and the most important operator is the diffusion operator. So we construct a heat equation on the complex network, on the graph induced by the complex network. So as we said that for the discrete vector calculus, this Laplacian is basically the Laplacian operator. And it is one can consider it as a div grad kind of operator, and so we have it like like if f is being diffused, the function that we are interested in, and then del f del t is equal to minus L f, that is what we can write, and we'll come to that, like how it is useful in our problem. So simultaneously, like in general, graph sparsification problem is defined as follows. So we have a graph H, and we want a sigma approximation of the graph, and then like the approximation, so LH of LG should be such that, like if you scale the Laplacian by sigma, then you would get something between the LH will produce in some sense we can these inequalities are defined in the sense of the spectral inequalities. We'll come to that. So either it is so something between the scaling by sigma and multiplying by sigma. Okay, so dividing by sigma and then square. So we are interested in this kind of sparsification. So basically a lot less complex network which can capture our reaction diffusion phenomenon. Okay, so an implication of the graph sparsification is that, like, we can take a look at the Courant theorem, and this has been widely used. Actually, the proof that that was there for the Kadison-Singer problem that clinched the answer to the problem also uses this kind of saddle point, like min-max theorems very generously, and it actually pans out in a linear algebra sense, quite from quite elementary spectral relationships. So so not surprising that we have to look at such relationships in the context of graph sparsification. And so it's well known that that the ith eigenvalue of a matrix A, and it can be defined as the mean max, max over the domain, sorry, the dimension and of the space, and then minimize over the vectors available in the space is transpose AX kind of relationship, if satisfying the saddle point. So, and now the graph sparsification can be can be defined more computationally, like computationally more meaningful sense, and so we are looking forward to the sparsified graph. We are looking forward to eigenvalues that would be like that would be lying between this this the original graph, same eigenvalue, like scaled by sigma, between the divided by sigma and multiplied by sigma. So so thus, if one graph is sparsified form of the another, they will have kind of similar matrices, because many of the eigenvalues can be just scaled up like this. So in that sense, you can call them similar. Okay. Now a little bit into the existing work. The cut sparsification was introduced by Mansour and Karger, and they have a much stronger notion. Although the much stronger notion is the spectral sparsifiers when the Laplacian quadratic form is preserved. But here the cuts are preserved in the Mansour and Karger kind of approach. So instead of the eigenvalues, you simply have these cuts and the cut values. So and they're between this 1 plus epsilon kind of scaling. Okay. Now, so here S is in the vertices and denotes the vertices of the graph G, and the cut is over the over this partitioning of the vertices, and it is defined in an usual sense. Okay. So then Spielman and Ting showed that every graph on n vertices has an epsilon approximation, and with only n by epsilon square order of ages, and can be computed in O m time, where m is the number of ages. And then Spielman and Srivastava, this is the work that was related to the Kadison-Singer problem, and showed how to construct an epsilon approximation, and with only n log n by epsilon square ages in OM time. So current approach of sparsification, which is feasible even for large graphs, is by random sampling of the ages, is so that it is done in a reasonable time. Though a deterministic approach is available, but it is not feasible for large graphs, as the deterministic approach actually overall time that is taken is OMN squared. So the quadratic thing, blows it up. So more from that same group, Srivastava, Spillman, and Joshua and Batson showed that a random deregular graph can be good approximation to a complete graph with high probability. And they introduced, they use notion of expander graph in the what is known as a spectrally themed tree. And this is put out in this sense, like you have a graph G, and there exists a spanning tree T, which is a beta approximation to the original graph G. And again, in the spectral sense, like the spanning tree Laplacian and is bounded above by beta times the Laplacian of the original graph. So this is important. This is because we want to approach along spanning trees in order to get our sparsified graph, which will behave in the same manner as the original graph when we solve the heat equation on it. So this actually says that any connected graph G of B has a spanning tree with spectral thinness of order of maximum, R effective, where R effective is a transformation. You can see that it is a root over of LG and root over of, so it is transformed by that. And AB denotes an edge of the graph, and LAB is corresponding Laplacian if you just have the two edges connected, the two vertices connected, and this square root term is actually not on the exact Laplacian of the graph, but since it's a transformation, and one has to get a pseudo inverse of the Laplacian metric. Because it's so we have to take a pseudo inverse. And so the R effective is the graph. So this produces sparsifiers with n log n square by epsilon square edges from the spanning tree of the graph by sampling edges. So this is not different. We'll be looking at how, basically that is the strategy to use solution. So by sampling edges independently, depending on the edge connectivity, I can create cut sparsifiers from random spanning trees, and the time for sampling is root 10 and sampling just two random spanning trees. This gives a cut sparsifier in bounded degree graphs and random graphs, and this is useful like when we design a sampling strategy. And so we try to answer like can we generate four spectral graphs from spanning trees, and can we approximate the flow in a complex network formed from non-random. First part, we first attack the first part of the thing, and then the second part. Okay. So there is a well-known technique, and we borrow from that sampling probabilities and sparsification resistances. So this was used widely by Spillman and Srivastava again, and so we considered the estimate like where the edge weights are are scaled by probability, and we evaluate an expectation that if you add them over the over this scaled age weights, then of course you get the graph of age weights, and basically you get towards Laplacian rows. And then how to select the probability thing, and that is we make use of the R effective here with that pseudo inverse of the Laplacian, and and we take a two the whole thing, and this is it for sampling for sampling. That once we do this thing, that thin graph, that is the thinned out complex network. How do we make sure that, like in some metric, I mean, it is carrying the same diffusion that we have targeted at before? So there is a very important theorem in data science called the Johnson-Lindenstrauss lemma. So whatever we do, we have to connect to the Johnson-Lindenstrauss lemma. Otherwise, the two things remain unaddressed. So that is like dealing with very high dimensional data, and then getting so getting the gist out of the data in the form of the sparsifier. So this is the fundamental work to do whenever we talk about a sparsifier of any data. And so if you have points in R d-dimensional, then you can have a transformation. So this is linear algebraic transformation, but it can be more complex. So we can have a transformation that maps it into a k-dimensional projection, and the k has a bound from the Johnson-Lindenstrauss lemma, that is 10 log n by epsilon square. And in some metric, here we have shown the 2 norm, but you can use other metrics, and it is in 1 plus minus epsilon. So this approximation and of the original metric on the RD space. So if one considers the graph as a like a Stifel manifold, and you have the metrics on it, then this follows that we can look at it in that sense. So here also we can define a Johnson-Lindenstrauss form, and this is the previous the RAB that we had put out in our effective can be computed in terms of this Johnson-Lindenstrauss form, and same with that with the pseudo inverse of the Laplacian. So we worked out a brief proof of that.
Sir, you are not properly audible.
Yeah.
Some issue with your connection.
Yeah. So
okay.
I think the network was
okay. Now it is okay. Now it is.
Yeah.
Yes, please.
Yeah. So this proof can be worked out in the sense of uh, linear algebra. So this is just manipulation, and so the whole
You are not audible, sir. I think there is some problem in network of Professor Laha. Talk to him. We cannot hear you. I think he lost his connection. Please hold. He gets back. So you are not still audible. Participants, please hold for a few minutes. Professor will be rejoining. Those slides are somewhere uh, still moving forward back here.
Okay. Okay.
Okay, okay. Yes, sir, you have joined now. You may reshare the screen. It's somewhere.
Okay. So.
Okay. Yeah, now you are audible.
Okay. So. Okay. So if we do have a spectral sparsifier G dash and of the graph G E on n vertices, and so let us have a set that is between Vi and Vn. Then then we can deduct derive the following relationships. And so for GLI denotes a subgraph of G formed by the set Li and that is bounded from below by the uh, by the summation over XAB, and this XAB we have defined before, or in the context of sampling, and then so we can have this is have these relationships is and these bounds. So basically the strategy is like we sample along the edges is in the neighborhood, looking for a branch with the maximum degree. Okay, so we just a second, yeah. So so we have an upper bound, and similarly we have a lower bound on this this sparsification on the on just like on one node and on its adjacency like on its adjacency list is looking for looking for the branch with maximum degree. So for example here this this GLI is that this is the branch on the that gets the maximum degree, and we move the theorem lets us move along that GLI. Okay. Okay. So since sampling edges by effective resistances produces a sparsifier with very high probability we know that when we delta psi is not a sparsifier of GLI, thus the sampling happens along the current branch GLI, that is the one with master degree, and
Sir, you are not again audible. We cannot hear you.
Okay.
So there is some problem with your voice.
Yeah, I don't know why. I mean, I have a full fiber connection, but still.
Now it is coming right.
The
there is some
yeah, the
intermittent
Microsoft
factor.
Teams is yeah, the Microsoft Teams is sometimes
Yeah.
just
Right.
trying to find a network. Yeah.
Okay.
Yeah. Okay. So as we said, like with high probability here means of the order of 1 minus 2 by n. That is the number of vertices in the graph. So this result is just like like a forming a sampling strategy. So we end up and then we can go on to prove it by contradiction that if the other bound that if the second unit doesn't hold, then it is implied that this along GALI we have we have a relationship that will contradict the upper bound. So so one can this is just manipulation, and one can actually prove that. So on a more interesting note, so we can see we can look at the Heffding's tail bound inequality, and for this is also useful for the devising the sampling strategy. So the deviation of the expectation and the estimates along the branch would be estimated by Heffding's inequality. So this is also another established technique in data science that comes in handy here. And a simple calculation shows that here the probability that will be deviating from the expectation and
Professor, again not audible. Professor Laha, you are again not audible. Can you try through the web app instead of the app, Microsoft Teams app? Can you try to some sound? Through web-based open Teams in Google Chrome or something else. Your slides are changing, but we cannot hear you.
Just a second, it's just stopped sharing.
If Teams app is making problem, you can try through the Google Chrome.
Yeah. Okay. Another, so in this set of relationships, another thing is that we can also get these bounds on the so along with the sampling and with the sampling with the hefting inequality and then finally we calculate on this Johnson-Lindenstrauss like relationships if on the smallest degree subgraph of G. And this is useful for establishing the sampling along the branches that we want to do. Okay, so as you can see in the proof, I mean this connects us back to the sparsification. So basically, it establishes all these relationships establishes as like a kind of interlacing between the scaled eigenvalues of the original graph from the spectra of its Laplacian, and that leads us to the the sparsifier basically. So okay. So we take the advantage of the upper and lower bounds of these inequalities and the framework now produces the co-spectral graphs only if we know the multiplicities of the eigenvalues. So this will be another problem, like why we cannot have a deterministic thing easily. So some of this, like along with this, this strategy that we have, because the multiplicities actually induce an NP-hard problem. So we'll come to that. Okay. Then
You need to share your screen again. You cannot see your screen.
Yeah. So can you see my?
No.
Okay. Again, I will reshare. Is it there?
Yeah, it's coming. Yes, it is there.
Okay. Yeah. Now there you have another problem. I cannot change the slide.
So instead of the Teams app, if you can open from Google Chrome or something, that probably can help. Because Teams is making some problem, I think, at your end. It's the same thing. Or reshare it, unshare and reshare it.
Yes. So I actually I can't change the slide. I mean, that is another problem. So
But
now it is
somehow
coming,
I
but
am
I
able
cannot
to
change.
change the slide probably.
Yeah. Can you
No.
change the slide?
Yeah, sure. I can change your slides. Okay.
Yeah.
Which slide were you in? Slide number?
Yeah, so about 19 or something. So go on scrolling. I'll tell you.
This is 20.
Yeah. No, so I cannot see of that. I'm not on 20. Okay, just a second.
On the computational and complexity. So participants, there are some technical issues. Please hold on. I'm trying to resolve it. Sir, please share your slides. Yes, we can see the slides. You are muted.
Yeah. Yeah. So yeah, now I've unmuted. I hope I'm
Okay,
audible.
I can hear you. Yes, yes, you're audible.
Yeah. Okay. Okay. I will
We're
just
discussing
come to the
about that
point. Yeah.
NP hard problem.
Yeah, yeah. So basically, this is how we connect to the the sparsifier, and also by using the via a relationship that is the Johnson-Linden-Strauss like relationship in the bunch of inequalities that we have, and these are obtained by sampling using the Hefting inequality along suitable branches as of the graph. So this will let us now build the spanning tree based thing. So we take advantage of this and move towards the move towards producing the co-spectral graphs, and but still will be limited by the sampling, because the multiplicities of eigenvalues of the Laplacian matrix induces some NP hard problem, and so if we have some prior knowledge of the multiplicities, then we may produce a characteristic polynomial and make we can do more on the problem, but otherwise we are stuck in an NP hard sense, and we can only produce some approximate result. Okay, so we have an algorithm that basically if uses the depth first search for moving along the graphs, and then does the sampling and according to the strategy that we developed using the Hefting inequality, like moving along from each edge, from each vertex, we move along the branch that has the highest degree, and then we make use of the inequalities that are Johnson-Linden-Strauss like inequalities is for establishing the algorithm. So this algorithm degree estimate for the co-spectral or interlacing. So how to get that that branch that along which we should move. Okay, then we can come up with an iterative framework. Okay, and this is the the minimization and between the degree and the expected weight that basically the derived from the incident matrix. So here we basically use the incidence matrix of the graph because that is that is so this comes from the second minimization problem comes from splitting up the the problem and splitting up the Laplacian of the graph actually, and and uh, and this is this gives us so this iterative framework lets us as show that use the positive semi-definite property of the Laplacian, and using that we can we can use like conjugated gradient kind of method to solve this problem, and the order of complexity is about n square log n plus m, and then we take the case spanning trees along which we solve this. So so from the so we move along the spanning trees that we just got from the other algorithm, that parameters from like we know now like with what branches we have to move along. And so then we compute some bounds on the worst case number of edges that we have to visit it in order to compute the complexity. And finally, we have to generate the whole spanning tree with these two results as in our kitty. So we can so in the literature we find an algorithm that that generates a spanning tree in the order of the increasing cost, and then there are algorithms. There is a plethora of algorithms that do better in time and space complexity. So and but generating all spanning trees is hard, and this is well known. And there's a small example in which which shows that this quickly that the number of spanning trees explode. So we are limited to the sampling that we have devised before. And so here our aim is to generate the spanning trees is along which the flow of the function fx that we are. So if you remember, like we have a heat equation that is propagating, and our sparsifier must preserve the flow in the end. So one can actually make a subspace expansion on the Laplacian of the graph, and from there we can collect collect a combination of the eigenvalues so that it is reduced to finding spanning trees with high algebraic connectivity. So this is important because then we can further limit our search for this such as sparsifier. So along with the movement strategy along the the highest degree neighbor at the highest degree adjacency adjacent node, and using the Hefting inequality for sampling the thing, and with equipped with the Johnson-Lindenstrauss like inequalities, and finally we try to find with the high algebraic connectivity. So the connectivity thing becomes important because of the because we are concerned with the heat flow. So this is where it slightly becomes a little bit different from the static graph problem. Like if you do not have a dynamics on it, then the sparsifier problem ends. Like you don't need to look for this connectivity thing, but since we want sparsifier that also reflects this heat equation, the diffusion dynamics on the system on this graph, we need the algebraic connectivity. Okay. So as we said, like so this gives us a like little bit of light at the end of this NP-hard tunnel, and then the so we basically borrow this so this kind of applications are there in free space optical networks, and some people have used mixed semi-definite programming approach, and then there are heuristic approaches and for maximizing the upper bound on the algebraic connectivity. So we can borrow any of these techniques from here and put it together. So in order to further further strengthen this connectivity thing, we borrow from a Steiner tree problem, and it is essentially involves finding the minimal spanning tree for the Steiner tree, and you have a lower. We are equipped with the lower bound on the Fiedler value, and then for minimal spanning trees, is the diameter will be less. Thus, our problem can be mapped to a Steiner tree problem. So this is the basic idea of constructing the like the heuristics that we will finally have. And since the size of the graph involved in real world complex networks can be huge, so we are limited to this kind of heuristics. So one can use simulated annealing for example, in the Steiner tree problem, and it involves like deleting k edges of a spanning tree of a graph, and there will be k plus 1 connected components, and randomly shuffle, then generate a path, and corresponding to each edge, we can select a random edge between the components u and v, and this can be done in a simulated annealing sense. Yeah. So the search space is random, and so here we can. So third point is more important. Computing the algebraic connectivity, and this is from the Fiedler value basically at each step, and it is computationally depending. So this is where the cost function is computed from the so this is where the cost function is computed after this this shuffling of the edges and this cost function is used in a simulated annealing sense. Okay, so here are some examples, and so this is an heuristics in which the cost function is like approximately calculated, and you can see that like in order to maintain the connectivity, we have to take care of the increasing of the Fiedler value, the highest Fiedler value we can afford. That is the second eigenvalue of the. So
Again, you are not audible.
yeah. So
you were not audible in the previous slide.
Yeah. So so basically the idea is to keep the like in the simulated annealing. So basically the idea is to maximizing the locally available Fiedler value of the subgraph, so that the connectivity is maintained. So that is the takeaway from that slide. And finally, the like there are many applications of it. So electrical flows, physical processes. Even right now, we are trying to have these things for, or like like for example, this infection networks, like pandemic processes and all that. So so another important application that may come up is like regulation of 5G networks, and because if there is a disturbance or an attack, that can be you know, like from the local, like the localization of the attack, and this can be a inverse problem in the sense of this sparsification, so that you basically trace in the trace quickly into that the center of the problem, and then localizing it or isolation of that part of the network. So for regulation of 5G networks, what we are discussing now is an important technique. Okay. So yeah, so then we like, you know, with doing all these things, we have to now connect it back to the, you know, this diffusion problem that we started with, at least computationally. So this is what we have already mentioned. This is the Laplacian operator here, and so next is, does it suffice to approximate the spectrum of the normalized Laplacian to approximate the hit kernel of a graph? And so the spectrum alone is not sufficient. We can see that from the analysis here, because this is where it again differs from a static graph, like, you know, from which a graph on which there is no dynamical process. Yes, and so okay, I again lost my slides. Like, you know, I don't know if it just keeps on going away.
Yeah, something is happening weird.
Yeah. So
Maybe you have to even share.
yeah, I just changed the slide and it actually went away. Just a second, it will come. Yeah.
Okay.
Yes, I almost at the end of it. I mean, sorry for, you know, like, you know, these interruptions. Yeah. Yes, and so okay, so just maintaining the spectral relationships, it may not be sufficient, and because there will be issues like in the dynamical process, for example, like stability or bifurcation, and that also becomes important. So we made a little bit of, so this, as I said, I mean, this is a work in progress. So some of the things are not, you know, like just preliminary results. So this portion of the talk is kind of that. So here we basically attempt a probability transition matrix. So a heat equation can be always viewed as a Kolmogorov forward equation, and you can readily connect it to the, you know, like a Markovian process. Yes, and that gives you the transition probability kind of thing calculation, and here we do that. So basically we compute the transition probability matrix, and basically do a little bit of matrix algebra and expansion of the exponential terms, to get the get a transition of, like, you know, like probability of transition of the signal, that is, you know, the fxt that we want to get. So now this has to be connected with whatever spectrally we have sparsified, and so the so there is an error term that can be computed between the, you know, like this just spectrally sparsified thing, and if you have the dynamics things that that has been propagating, and here to further augment the spectrally sparsified, you know, graph, what comes in handy is the idea of a proper orthogonal decomposition, which is similar to a singular value technique. So basically to find out, like, you know, the important like, if you have a option of the spectrally parsified things that we have computed from the heuristics that we just described, how, like, which one to pick. So basically, so you can see that there is like a covariance kind of matrix in R, and this can be decomposed in similar to a singular value or a principal component analysis kind of thing. And once this is done, so this can be put back. The row can be, the row is like, like there's a dimension reducing thing, and that can be put back into the equation to get a lower dimension equation. Okay, so on the sparsified thing and the sparsified graph, and we can see that whether this behavior is close to the behavior of the original graph in the probability transition probability sense. Okay, so that's what we do, and this POD thing is well known in generally in computational mathematics and scientific computing. So that's exactly what we do, and so basically we connect it back, and we actually get a new new problem on the new dynamical problem. So that is the last equation, the new dynamical problem, and new here diffusion problem on the sparsified graph. So this is the concept basically. Pairwise is comparing the flow with the sparsified network and the original network. And okay, so here we so that is the discrete view of the thing, and it can be shown that it is nothing but a numerical technique called the Runge-Kutta method. So it is similar to, the calculation becomes similar to a Runge-Kutta method. Right. Okay, so so some more of these relationships. I mean, this is just for showing that we have the right thing, and so one can view it as a like a Lagrangian framework, in which again you can see that there are, this is the objective function, which is like which is the minimization of the error between the response of the sparsified graph and the original one. And yeah,
So there have been some added iterations in the presentation.
yeah, I don't know. Yeah, so the Microsoft Teams is just not behaving. I mean, my connection is okay. It is just it is working at 150 Mbps, but this one is just Microsoft. I think it has its, maybe too many people are there and it is dropping. Yeah. So okay, so we'll just come to the almost, we are at the end of the talk. I will just finish it with the reference to the 4D var method, and so one can actually compare these these pairwise objective functions, hence in this what is known as a 4D var sense, and this and to finally select dynamically the sparsifier that is closest in dynamics, I mean not just in the spectral sense, to the original problem. One can use this 4D var, and this is a standard technique, and one can the once the Lagrangian objective function is set up, one can solve it with the steepest descent or conjugate gradient or any other method that is that would be performing well. So we did some we did some simulations, and so this is the comparison of solution obtained after. So this is a small graph that ABCD and this is a toy graph, toy problem, and we applied that sparsifying thing and basically one can see the the heat equation that is being solved. So comparison of the solution obtained after correction of solution of POD, where so we have these 4,000 observations, and number of principal components is 4. So it is a toy problem, and you can see that from the 5 node to if you want to get a 4 node, the sparsified graph is only 4 node, and still you have the like with the POT we can get close to the behavior of the original graph. Okay, so some more like example. So this is called a chemical brusselator model. So this is a chemical brusselator like a chemical reaction that is spreading along a complex network. Okay, these are important in pollution control sometimes. So we have the similar like simulation and how we converge to a from the converge to a sparsified graph, and as we let the as we move towards a very like a more and more sparsified graph, I mean you can see that the error increases, and it especially the jump here that occurs earlier. And if we allow it to be dense and more dense, then it kind of goes to the goes back to the original problem. It is when so this is like these are calculations just in context with that. So basically what the takeaway is that we are attempting this this basically this sparsification of reaction diffusion networks, and so these are useful in many contexts. I mean, I just mentioned 5G networks and also infection dynamics and all that, and so the additional thing that we do here is not just the sparsification in the classical sense. We also the spectral sparsification is connected up with the with the time diffusion problem, that like the temporal moving thing, the diffusion heat equation that is that is operating on the graph. So so basically we have post-spectral graphs for certain undirected graphs, and we computed interlacing polynomials, and then we had a computationally efficient framework in which we connected it to the dynamics, and some toy examples we computed, and so this is a work in progress. We hope to do more on it. Okay, sorry for repeated disconnection, but I just tried to give you a glimpse on like what some of the newer problems in data science. Yeah. Okay.
Thank you, Professor.
Yeah. Thanks.
Connecting a lot of.
Yeah.
So audience, if there is any question, you may raise your hand. Then you can ask. Okay. Before they ask, I have some questions.
Yeah.
For example, like for this 4,000 observations, if you go back to spanning tree, what will be the size?
Okay, so we.
In the toy problem, actually.
Yeah. So we have it here. So. So it would explode. Actually, it will be like, so for this one, we calculated like, so this is, so it would be the order of the, like, so you will have many spanning trees. So this basically, so you have to like.
And is it possible to actually handle the spanning tree in this case of
Uh,
this in terms of memory and resources?
No, it is not. So that is the thing. I mean, for a toy problem, you may have like, this had some 90, like, like some 9 lakh spanning trees or something like that. We calculated. So
But
various.
for any realistic problem, then full spanning tree.
No. So that is the whole thing. That is why this, this heuristically sampling and sampling in the sense of this Hefting inequality and basically using this Johnson-Lindenstrauss bounds for moving along the sampling paths in the graph. To find and maintaining the algebraic connectivity as much as possible to generate the selected spanning trees. So these sample spanning trees, I mean these heuristically generated spanning trees, these we then examine in with a POD or a 4D var kind of approach to connect it to find the one that is best, the nearest to the dynamics that heat
So
equation.
what is that sample size which you were examining? Right.
Yeah, so here it was like some 4,000 samples or something so that we are faced with.
Okay.
Yeah.
And in that sense, like these computations, are they costly?
Yeah. So basically, it depends on like like to what extent you want to match the result. I mean, and what is the size of your like sparsified graph? I mean, so if you can. So basically, in the dynamics, if you have nodes that will actually receive very little of the, so think of a time window in which this diffusion has happened, and there are some nodes to which it will almost not reach. The diffusion will not reach within that time window. So now we can curtail the size of the like the network. Basically, even the spanning trees are pruned basically, and there you can generate something that is that is computable, and so it is something like that. And so when you look at so dynamically when you basically iterate and move, you basically generate the spanning tree that is not even the whole network is spanned actually. So for very large problem, it will be just within and like the nodes that are having very low transition probability that we need not even visit. That will automatically be pruned out. Yeah.
Okay.
Yeah.
Thank you. I think
Okay. Yeah. Okay.
participants are exhausted.
Yeah. Okay. Okay.
Throughout
Thank
the
you
day
very
they
much.
are
Yeah.
leaving.
I'm
Thank
sorry.
you very much, Professor. I
Yeah.
talk to you later.
Yeah. Okay. Thank you.
Okay, so for the participants, we'll again meet tomorrow morning 10 a.m. We'll have talks on GPU technologies from NVIDIA. Thank you all. Thank you, Professor Laha.
Thank you very much.
Yeah, we call it a day.